three more concepts we are going to cover here are very important when we talk about implication. The first one is the concept of a converse of an implication. And when you take P implies Q, the converse is Q implies P. Okay, that is the converse. How you obtain the converse is obvious here. You just change the antecedent and the consequent, and you obtain the converse. The inverse of the implication is given here. What you do is you negate both the antecedent and the consequent. So the implication, the original implication is P implies Q, and the inverse is not P implies not Q. Okay, and when you combine these two, you obtain what we call the contrapositive. Okay, so you take the inverse of an implication, and whatever you get, you take the converse, or you can also do it the other way. You take the converse first and then take the inverse. So you take P implies Q. Let's say you take the converse, you get Q implies P, and then you get the inverse. What you get is not Q implies not P. Or you take the inverse of the original implication, not P implies not Q. You take its converse. What you have is not Q implies not P, the same statement. And that we call the contrapositive. Why is this important? Because if you observe the truth table for all of these, it's obviously we have four input combinations here, and this is the original implication. And you write the converse here and the inverse here, and you obtain the contrapositive here. And when you look at the contrapositive and the original implication, you see that they are equivalent. This is extremely important because there is a method, a proof method, which uses this proof by contrapositive. Instead of proving an implication, you prove its contrapositive, and then you argue that they are equivalent, so the proof is complete. So this is very important. Obviously, when you look at these two now, the converse and the inverse of the original implication are also equivalent because, well, they are essentially contrapositives of each other. Okay, here's an example, again, similar to our previous example. Let's assume P represents this is a fish and Q represents this swims. Now, this is the original implication. If this is a fish, this swims. And if you take the converse, that's Q implies P. If this swims, this is a fish, right? Now, in the general sense, obviously, this is true. If this is a fish that swims. On the other hand, you see the converse is not equivalent. If this swims, this is a fish. This is clearly false. Right? There you see, the converse is not equivalent to the original implication. But obviously, it's contrapositive to the inverse of the original implication. Therefore, it's going to be equivalent to this one. And that's the same as saying if this is not a fish, this doesn't swim. Right? And finally, you get the contrapositive. If this doesn't swim, this is not a fish. Okay, I would like you to think on this statement and really observe why that is equivalent to this one. Now, we have shown it symbolically via truth table, but through this example, I hope it will become clear why this original implication and the contrapositive are equivalent. Essentially, what we are saying is saying if this is a fish, this swims, is equivalent to if this doesn't swim, then it's not a fish. So those two are equivalent statements. Right, now we have covered the implication, And we can talk about actually the biconditional, which is a conditional that goes, as the name suggests, both ways, right? So P implies Q, but at the same time, Q also implies P. Now we call this logical equality because you see this reads P if and only if Q. Now the implication goes both ways. Now recall the definition of implication. Implication is always true except for when the antecedent is true and the consequent is false, essentially this. So in this case, P implies Q is false. On the other hand, when you take Q implies P, that will be false when the input combination is this, right? Therefore, you see the conditions when the biconditional is true reduces to two, where both of them, both of P and Q are false, or both of them are true. That is the reason we call biconditional also the logical equality. So in mathematical texts, you will come up with if and only if, or an if with a double F very frequently. And this is what it means, a logical equality. P, if and only if Q. So they have the same truth value. Either both are false or both are true. Now, essentially, this is equivalent to saying the biconditional can be rewritten as P implies Q and Q implies P. So that's a sort of a simplification of the biconditional. Here's a very simple example. P, 10 is divisible by 2. And Q is the proposition 10 is an even number. Again here, P implies Q and Q implies P are true. Hence, the biconditional is true. Okay, so in this case, P implies Q and its inverse and also its converse and naturally its contrapositive are equivalents, right? But this is only when they have logical equality.